Okay, this is a standard RLC series circuit. The source voltage 200 volts applied to resistance, inductance, capacitance in series. We are asked first to calculate the impedance. So we'll start off by saying that XL equals 2 pi times F times L. The frequency is given as 60 Hertz, and so that allows us to say 2 pi times 60 Hertz times the inductance value of 0.8 Henries gives us XL is equal to 301.6 ohms. Now next we would like to calculate the capacitance. For capacitance then XC equals 1 over 2 pi FC, and so we have 1 divided by 2 pi, 60 Hertz, and 10 microfarads. Now remember then the micro means 10 times 10 to the negative 6 farads, or 10 exponent negative 6 farads. And so when we type this into our calculator, we should be able to come up with XC equals 265.3, and the unit for capacitive reactance is ohms. Now, remember that the inductive and capacitive reactances are out of phase with each other by 180 degrees, which means that they cancel each other out. Now in this case, because XL is greater than XC, that means that this will be an inductive circuit overall. And we wish to calculate now the net inductance. And the net inductance is always the difference between XL and XC, and in this case then XL subtract XC, and it will be net inductive. And so we have then 301.6 subtract 265.3, and X net becomes 36.3 ohms. Now, we are not asked to sketch the impedance triangle yet, but remember that if this circuit is inductive, our impedance triangle basically has R, X net, Z, and theta. Now, I won't label it with values, but the idea is that this illustrates that the impedance by Pythagoras' theorem then, R squared plus X net squared square root. So we have the square root of the resistance was given as 30 ohms squared plus X net 36.3 ohms squared. And if we work that out, we should come up with an impedance of 47.1 ohms. Z then 47.1 ohms. And so as we said here, XL is bigger than XC, and that makes this an inductive circuit, which means that the power factor will be lagging, the phase angle theta will be lagging, and that we will draw the phasor diagram and the impedance triangle as lagging diagrams. Okay, so part B asks us to calculate the current, and now that we have the impedance in the circuit, of course we can apply Ohm's law with the source to say that the current is equal to E divided by Z. And that gives us 200 volts divided by 47.1 ohms for a current of 4.25 amps. Now that current then goes through each device in the circuit. Part C asks for phase angle and power factor. And so the phase angle comes from the impedance triangle, and we can write that now as 10 to the minus 1 of the vertical component, which is X net, divided by the horizontal component, which is R. And so theta is 10 to the minus 1 of 36.3 divided by 30. And that gives us 50.4 degrees for theta. Remember, it is a lagging angle. When we calculate theta and power factor, we should always indicate leading or lagging. The power factor then equal to the cosine of theta, or the cosine of 50.4 degrees, and that gives us 0.637 for the power factor. Again, we should specify that it is lagging. Now, D asks us to calculate the voltage across each component, and typically that means that we will do each component individually. And so as we can show then on the circuit, we have VR, we have VL, and we have VC. And you know, sometimes it might be acceptable to use the net reactance here to calculate V net, but remember, in this case we have been asked to calculate the voltage across each component, so we should do it for all three components. And so for part D then, using Ohm's law, VR equals I times R gives us 4.25 amps multiplied by 30 ohms, and so VR 127.4 volts. VL equals I times XL, the inductive reactance. We have 4.25 amps multiplied by 301.6 ohms, and that gives us 1282 volts for VL. And notice that that voltage is larger than the source voltage, and that sometimes happens in RLC series circuits. And so allow us to carry on before we finishes our discussion on that one. Think about the voltage across the capacitor as I times XC, the capacitive reactance, 4.25 amps multiplied by 265.3 ohms for a voltage of approximately 1128 volts. Now, again, that one is bigger than the source voltage. Kirchhoff's voltage law, or I guess the laws of series circuits, kind of reminds us that the largest voltage in the circuit must be the source voltage. But here, with these circuits, remember, vector addition applies to the summation of the voltages, and VC and VL are 180 degrees out of phase, so they kind of cancel each other out. So if we calculate V net, which would be the voltage drop across the combined reactance of the inductor and the capacitor, which is V net basically, remember that V net will be equal to VL subtract VC, and we have 1282 subtract 1128, or 154 volts, which is indeed smaller than the source voltage. In addition, we could have said that V net equals I times X net, which we had calculated earlier, and that will give us a voltage of approximately 154 volts as well, if we did that calculation. Now, part E asks us to sketch the impedance triangle, and we made a brief, or crude, shall we say, sketch of the impedance triangle above, but now we will sketch and label it. Remember, it is a lagging triangle. Typically with impedance triangles, I do not include the XL and XC. It doesn't really make it a triangle. It just puts the X net value on the triangle when I do impedance triangles. And so for me, the impedance triangle would basically include the resistance R equals 30 ohms, the net reactance, which in this case is inductive, so X net is equal to 36.3 ohms, gives us Z at 47.1 ohms. And remember, the angle theta, or the phase angle in degrees, 50.4 degrees, should always be shown, and we should indicate the right angle down there in the corner. Okay, part F now asks us to sketch the phasor diagram. The phasor diagram is a little different. It's not really a triangle, and so on the phasor diagram I would expect to see the voltage across each component shown, as well as the current and V net. And so for the phasor diagram then, let us include the current as the reference. I equals 4.25 amps, and yes, 4.25 amps. And so now we should also include that VR is in phase with the current, and so VR at 127 volts, let's say. VL was difficult to draw that on the scale, isn't it? But VL is equal to 1282 volts. VC is 1128 volts, and that produces a V net, I suppose, if you would, which would be the difference between VL and VC, which kind of gives us V net here at approximately 154 volts. And so V net plus VR should give us the resultant E equals 200 volts. The angle in here should be theta at 50.4 degrees lagging. And so we might want to point out that for this question I've used E for the source voltage. In Ohm's law I have used E as the source voltage. The circuit provided for this question says V source there, but of course the source is often labeled E. There's usually puts a label of E on there for that source voltage.